Get it out.
Okay.
Today we're going to wrap 15.5, and then we're going to do 15.6.
When's
So-
your test gonna be?
We'll discuss that here once we finish everything up.
Okay.
Do you need help?
No, I want to line it up perfectly.
Okay. So, the mean absolute deviation, and it's been a couple days since we talked about this. So the mean absolute deviation. What does deviation mean? So Jaslyn, what does deviation mean? Deviation. Like difference, right? If you are deviated, you are different than something, right? Different than whatever. So when we talk about means, what is a mean? Julian, what's a mean? In math, what do we talk about mean? A mean. What does mean mean? That is not mean. Mean is the average. Now, which is most occurring? You kind of set yourself up on this one. What most occurring is that MO, mode. So most occurring is the mode. So the mean is the average. So our mean absolute deviation. Now, where's absolute come into play here? Why do we use the word absolute, Andrew? Has to be positive values. We don't care if it's below where we're referencing. We don't use negative numbers. We're talking about distance. So we talked last week about how we calculate the mean absolute deviation. We find each of the deviations, add them all up, divide by how many there are. So when we're looking... we're going to the back. I'm getting there. I'm doing review because it's been a few days and the weekend. When we talk about overlap in data set, it's trying to communicate something. So statistics is all about communicating information based on data that is collected. If there's a lot of overlap in the data set, there's less mean absolute deviations between them, and that means the data is more similar to each other. If there's a greater distance between the data sets, there will be more mean absolute deviations between them, and that means that the data is less related or not related.
Wait, how do you find the mean absolute deviation between two data?
So we compare, so we first found out, up here we found out their mean absolute deviations were approximately 2, didn't we? Check your work from the 1.9. So it says round to the nearest whole. So the mean absolute deviation here is approximately 2. So that means every distance of 2 is a mean absolute deviation. So we then look, that's boxes lined up right on top of it, so now it's going to get confused. So then we say, what is the distance between the centers of our data? So we say that our center of our data here is about 3.5 and 10.5. So those 7 mean absolute deviations, that means that there are 7 mean absolute deviations there. These are 2 different things. So realize that this is heights of second grade students. This, I don't know what data is being communicated here.
So they find the mean absolute deviation between 3.5 and 10.
Yeah, so the big thing is realize that that mean absolute deviation of 2 is not the mean absolute deviation that we use down here. So these are 2 different things. So here, if this is 7 mean absolute deviations, these are showing you, like these values are showing you the deviations, the mean absolute deviations. It's not showing you like height or pets or, you know, what that's communicating mean absolute deviations. So this will make more sense. Let's do a couple on the back. And you'll start to understand this because when we relate it to real situations. So we're collecting data on heights. Let's say one of you took your discovery day, you went to an elementary school, and you collected data on 2nd graders. Then you came back, and you collected data on 7th graders. So do you think there could be some overlap in the height? Ignore the graph. Just what do you think? Do you think there could be overlap in heights between 2nd and 7th graders?
Maybe?
Do we have some pretty short 7th graders?
Yeah.
Are there sometimes some pretty tall second graders? Yeah. So this little red dot here is a really tall second grader. This blue dot here is a really short seventh grader. Purple dot.
It's a purple dot? That means they're both the same. Yeah.
What do you mean they're both?
Like, okay, so you got the second grader. So one guy, he's like 57 inches, and then one seventh grader and one second grader, they're both going to be like 57 inches tall.
This dot is both red and blue. So this dot is both red and blue. So that's representing two kids, a second grader and a seventh grader. I'm going to pause and start. That thing down at the bottom kept kind of coming back and forth. So hopefully this is fixed now. So we've been told, highlight, underline, circle, star, the mean absolute deviation for each set is 2. If we wanted to calculate it, we could, because they tell us the mean for the second graders is 50, and the mean for the seventh graders is 61. So then we could look at each of their deviations, add them all up, divide by how many there are, and we get approximately 2 for both sets. So I then reference from my means. So from your mean, wrong color. So if you're highlighting with me, I'm going to say my second graders are yellow, so there's their mean. And my seventh graders are blue, there is their mean. Notice that your average, your mean, doesn't always happen at the mode. The mean and the mode are not necessarily the same thing. Often they're not the same thing. So here in my seventh graders, the mean and the mode are the same. Did that happen to my second graders? What's the mode?
49.
49. And the mean is 50. So still the data's really close. When the mean and the mode are the exact same thing, that tells you your data's pretty well centered, because there's some above, some below, but they average out to the same value. So if we want to compare mean absolute deviations between them, what is the total distance between their averages? Ozzy? 11. What would we do with that total distance to figure out how many mean absolute deviations are between them? How big is a mean absolute deviation here? 2. All we do is divide that by 2, and we say there are 5.5 mean absolute deviations between them. I know. Some people didn't write it down. We were at the end of class. I'm reviewing. So, in the got it, try that on your own. Which is why I wanted to review that with you guys. Because if I just said, hey, we already did this, try that on your own, you'd be like, what? That was it last week.
162 is only
Hmm?
62 inches is 1 dot per purple.
So each purple dot is representing a blue dot and a red dot existing on the same thing. Because they don't want to stack them, because that would incorrectly show, like, you would think there was more. So there's 1 blue dot here, 1 blue dot there, 2 blue dots here, 2 blue dots there. There's also 1 red dot there, 3 red dots there, 3 red dots there, 2 red dots there, and 2 red dots there. But that doesn't really matter with what we're trying to answer, because really the less mean absolute deviations between them, the closer the data is to being the same. Obviously, we know heights of second versus seventh graders won't be the same. That's a decent difference between them. Predictions. Do you think there will be more or less variation between the sets comparing 7th to 9th graders? No?
I think there's going to be less.
Why?
Well, I think that because 7th and 8th graders are only about...
7th and 9th.
Or sorry, 7th and 9th. I'm just comparing 7th and 7th and 9th graders are only 2 years apart from each other, and so their bodies have matured around relatively the same period of time. I would expect there to be a few like 9th graders to be taller than 7th graders, but I expect them to be closer because there's a bigger jump from 2nd to 7th than 7th to 9th.
So we would expect to see more overlap, which we already pretty much communicated by looking at those purple dots. Every purple dot is an overlap, is the same value at the same place, and actually they overlap completely between here all the way up to the last red dot here. So you've already done some homework like this. Hopefully you've already done this homework, where it talks about, or it asks you to talk about the overlap. And here we would say, well, my values, my sets overlap from 59 up to 68. They share values all between that range. But we're not just talking about overlap. We're talking about the absolute deviations. So, Anish, how much variation is there between the averages of the two sets? Just how much variation? Between what values?
Between 61 and 66.
61 to 66, there's a difference or a delta of 5, difference between the sets. We use delta a lot for difference. So then what'd you do with that 5?
I divided it by 2.
You divide it by 2 because they both share the same mean absolute deviation. And you got 2.5 mean absolute deviations.
What if they had different maths? Like what if the 9th graders were
It then gets very difficult to compare the data sets. If one has a lot more variation away from the mean than the other, you do some other strategies. Most of what we'll work with in 7th grade statistics, pretty much everything we work with, the maths are the same or very close to each other. Like, if one was 1.5 and the other was 4.5, we probably just wouldn't be able to compare them like this. So we already pretty much discussed. You could write down if you would like. Be ready to give a short answer response on like an assessment. But just talking about what can we say based on the two different mean absolute deviations between the sets. So one had 5.5 between them. The other had 2.5 between them. So the smaller the mads between them, the more overlap that we're going to see. That's really what we would want to say there. So when we compare data sets A to B, or B to C, or A to C, well, let's look at A to B. That number line is showing you mean absolute deviations. It's not showing you heights or anything like that. It's showing you mean absolute deviations. So they're starting saying that the average of the data set was right here. The mean, the average, whatever. Or here. Or here. And you can highlight circle star. Whatever you want. Lower the number of multiples, more overlap. Higher the number of multiples between them, the less overlap or no overlap. So the last thing to wrap up 15.5 here, try to sketch a curve down here that would be 4 mean absolute deviations away.
What?
So we're told the mean absolute deviation is 25 of this set, and the average of it is 300. So this curve is set with an average at 300, and we know the mean absolute deviation is 25. So if I started to draw like dotted lines at my deviation sections, well, if I go 25 away, that would be a deviation. If I go another 25, that would be another deviation. If I go another 25, that would be another deviation. And by the time I get to 200, I've gone 4 deviations from the mean. Well, what I'm trying to do is sketch a curve that is 4 mads away. How far is 4 mads?
1.
It tells me what 1 mad is.
25. Oh, so
25. So 4 mean absolute deviations
that would
is going to be a change
100.
of 100. So I get to cheat. I'm going to draw the exact same data.
Why?
Oh. Just draw dots.
then I can move mine.
Bro, cheats. Bro.
Or I could go my next data set higher than this data set,
Can I go lower?
and I could scoot it to the. Yeah, my green went 4 mean absolute deviations lower. My blue went 4 mean absolute deviations higher. Doesn't matter which way I go, I'm 4 mean absolute deviations away. So yours would just want to be something similar to that. My data is concentrated in the middle, so I have a higher point there. And then I have a few more at 200 and a few more at 400. So if I shift my data, I'm trying to think what this could communicate with. Hundreds.
How many centimeters?
Jelly bean.
I was thinking like money you got for your birthday or
Jelly
something
beans,
like
that's a
that.
Jelly Belly factory. How many jelly beans?
Alright, any other questions, comments, concerns? 15.5. Who needs 15.6? I don't know how many of you guys are realizing that sometimes I set it out. You need 15.6? I am actually, will you hand these out for me? I'm going to stop and save this video really quick so I can start a new one for 15.6.